Well, hi everyone. As Tillman said, I'm not Alisa. So this is not Nginx, but it's going to be Android exploitation, Android kernel in particular. Well, I work for this company that you may have heard of, which is called Bluefrost Security, which is why I'm the last-minute replacement of the talk. The bug or the talk is a bit of a story about. Oh wait, sorry. Does this work? Yeah. So I know I have to talk since 2 days ago, so please be nice to me and stuff. Yeah, the slides are prepared for a while before that anyway. So it's a bug that we found in mid-September 2018, and some other people also found, and we spent considerable time and frustration just working through it, and I'm going to share a bit of that with you guys. So it's a local privilege escalation on Android. We had an exploit for this Pixel series. We tried 1 and 3, I believe, maybe even 2 as well, and Galaxy S9. And it's a bug in a driver that will sound familiar to you. Anybody heard of Binder? So we'll go through that in a moment. So the first part of the talk is going to be a bit of introduction and warm up with details about Binder. So Binder, in case you didn't notice yet, it's the main core IPC mechanism of Android. So there is a kernel driver that performs the transport part of the driver. So it's in charge of sending messages from one side to the other and orchestrating all this. And then on top of that, well, there is the context manager, which is in the Android world is called service manager. And this is basically like a service directory, like when you would call to the cable person and say, connect me to this number or whatever. So you basically can ask the service directory, I want to talk to the context service. And it will give you a reference to that contact, and you can talk to it from that point onwards. And on top of that, there is a bunch of libraries that provide the transparent remote procedure calls and object serialization. And the interesting thing of Binder is that it's accessible for every process in the system, including the Chrome sandbox and Firefox sandbox. It's just accessible to everything on Android. So that makes it a potential target for sandbox escapes. So how does this work? One sec. So there is a sender process, which is up here, and there is a receiving process down here. This receiving process has a mapping. This is the blue buffer that's managed by the Binder driver. So when you want to send a message from one side to the other, you make the data that you want to send and some metadata, which is this offsets part here, and you prepare it, and you make a structure that point to it on your own address space. So you basically say, here is some data, here is some offsets. I want to talk to the service with this number, this handle, and I want to ask it to do an action that's transaction code 1. Now that goes to the driver, and the driver will take this and will basically translate these things or like validate it and translate, etc., and will copy them over to the other buffer, to the destination. So at this point, the destination can see this translated and validated and whatnot content, but it has to read a transaction to receive it, to want to receive it. And when he does that, it will get a similar structure to the one we started with, except that the service handle here has been converted down here into a service pointer. Okay? So that's part of what the driver translation process does. It translates handles into pointers, and we'll see what else it does. So yeah, this allows us to send data from one side to the other with an action code and some objects. Now, what is in that transaction? What are those offsets, right? So in a transaction, there can be just opaque data, which has no format. It's just the driver doesn't care about it. And there can be objects at different offsets within the transaction. So the offsets array has offsets into the transaction at which the driver is going to find objects that it has to translate. And those objects can be of different types, including file descriptors. So it will just send the file descriptor, the same as if you send them through a Unix socket. It's the same thing, it just appears on the other side. And file descriptor arrays, there's just many file descriptors. Then there are Binder objects, and these are, like, for example, the services. They're a Binder object. They start on the sending process as an object, and when you put them in a transaction, they become a handle, which is an opaque number, such that the other side doesn't learn this, whatever object it is or whatever it could be. But instead, it will be translated into a handle that's process-specific. Now, for each of these objects, there is a Binder node, which is written up here. This is a structure that's reference counted and represents this object for the whole system. So anybody who has a handle to this object will somehow know that, or binder will know that it refers to this particular object. And it only keeps one copy of the object, but then as many handles as needed. And if you send handles, then it depends on whether you send the handle to the owner of the process or to another process. If you send the handle to the owner of the process, it will translate it back into a binder. If you send the handle to yet another process, it'll translate it into a new handle for that process. And in this way, you can just send objects around the system such that binder knows, or actually that the original owner of the original owner of this object knows if it receives that object or if it receives something else. And you can use this also as a kind of a token to pass around for permission checking and things like that. So, okay, we have this buffer. We send this buffer around, and there are some objects in there. And then when we're done with the buffer, the driver has to clean this up somehow. So when we give it back to the driver will take a look and see that there is a target node. So who did we send the transaction to? And it will drop a reference on that. Then it will check all the objects in the buffer and release any kind of references that are in there. And the same will go with file descriptor arrays. It will just close every file descriptor in there. And this, of course, allows for reusing our objects and not having just a growing list of, or a growing buffer that is indefinitely growing. All right, so we start with the bugs. These are bugs that we actually fuzzed. The first bug is, you probably, I don't know if is it readable from, oh, wait. Is it readable from the back? Yeah, okay. So it's a use after free bug in Binder, and you can see, well, down here, the thread stack that allocated it, Binder transaction, and if you would scroll down, you would see who is using it now and who freed it, right? So what do you do next? You try to figure out what this bug is and what happened. So you go to the place who allocated it, to the place who freed it, and you know what's happening here. Why is this happening? So it turned out that it was a race condition, like many other bugs that are showing up these days. And the race condition was related to this allow user-free variable that you see up here. So what's happening here is on one side, on your right side, also mine like this, you see the thread that's receiving a transaction, a one-way transaction, and on the other side, thread number 2 is the thread that's trying to free a buffer, a transaction buffer. Now, when this is written, this is lockless. There is no locks here. So when this is written to 1, this guy can go past this point. Yeah? Agreed with that? Now, when we get to the else branch here and come here, then the transaction buffer, it will be checked, and if it's existing, then it will remove a back pointer to the transaction to prevent use after free. And then it will k-free the transaction, right? What happens, however, is that if this check happens before this check, then we see a transaction buffer that's not null. But then if the free here happens before this particular point in time, we're going to write a null pointer at an offset from a transaction that has just been freed. Does that make sense? Now, you could say, like, you may think that this is not really, that the k-free will take much longer than this guy to come from here to here, but, you know, like preemption, etc. Also, it turns out that this lookup is cached in a register, and therefore here there is no memory dereference anymore. So that also increases, like, you're not fetching the pointer twice, and therefore the second time you don't see the null. So it gives you a little bit of a bigger window again. Anyway, this is not the bug I'm talking about. Because we looked at it, and yeah, the window was pretty small. There's no really time to preempt this thing. There's no API there that allows you to preempt the reuse path before, like, you know, to make the window bigger. There is no way to go to user space or no logs or anything happening there. And you can only write a null at a certain offset, which is useful, but if you add it to all these other conditions, then we had the feeling that we could look for something better, right? But I still wanted to make sure that this was actually the bug that I was triggering with the fuzzer. So I made a POC for this. And you know, I made some semi-random racing between these two conditions, and I just ran it for a bit. And immediately started seeing crash logs. Different from the original bug, actually. So this is bug number 2, which the fuzzer also found, but like a week later. This is a kernel bug, and if you're familiar with the Linux kernel, this doesn't mean that there is this doesn't necessarily mean something really bad. It just means you violated an assumption that the developers encoded in a sort of assert. Okay? So what assumption did we violate? Well, we violated the fact that we're freeing a buffer for a second time, and it was free. And again, when we look at it, it's, again, with the culprit with the allow user free variable, which is also unlocked. The update is unlocked, and it turns out that when this buffer is returned from the allocator, if the buffer was ever used for a previous transaction, it already had this flag set to 1. So this gives me a window from this point to come in and free this buffer and pass this check. Yeah? So now I'm going to have a transaction that's processing a buffer and a transaction that's freeing the buffer at the same time, the same buffer. So this transaction will probably do something weird with this buffer. There is one thing, these buffers are not necessarily kmalloc buffers. They are just in the vmalloc space, and it's not like a heap use after free just yet. So yeah, this is the bug that we're going to talk about. And it's going to be probably a bumpy ride, so let's see. The thing is, at this point, I went to a party, yeah, I spent some time in the flight just trying to trigger this bug in a more controllable way and trying to find something interesting with it. Yeah, I just got random bug checks everywhere, and I couldn't get past those in any way. And my mood was, if you ask some of my colleagues, it was like, yeah, no way I'm going to exploit this in a reliable way in this kind of bug. But luckily, I have colleagues. So somebody stayed working. That was colleague Jordan. He's around, I don't know where. He had a good idea during that week, so he stayed back home. He worked on this. The idea was related to basically sending a fake transaction first with fake objects, so preparing the transaction with fake objects first, but not passing an offset's size. So you say there are no objects to the binder driver. So the binder will treat this as pure data and just put it in there, right? Now, if we free this, so we receive the buffer, we free it, and now it's available for the next transaction, but the data is not cleared. It stays there. So now we have some fake objects sitting there. Now, if we try to now create a new transaction in which we tell the driver that there is actually offsets, but we race with the bug, what will happen is that the free path will release objects that were not validated by the driver. So it will release objects with arbitrary contents. And therefore, we can free fake objects. Yeah? But these are not objects, as in like kernel objects. Yes, it's not an arbitrary k-free. It's a release of a binder object from the transaction. So let's see what that means. But first, well, with that particular POC, what we had was that this binder type FDA, so a file descriptor array, was being freed prematurely with uncontrolled data or unverified data. And that thing has a parent buffer, which we then controlled. So that's a pointer, which points, in this case, into userland, but then the kernel does some computation to compute the kernel alias of this userland pointer, and then it dereferences it here, down at the bottom. So basically, with this POC, we could basically read from semi-controlled addresses and close semi-arbitrary file descriptors, if we could do this. But there is more switch cases up here next to this one that may be more interesting, right? So this means, as I said, we can force the release of fake objects. One of them is valid file descriptor arrays. And actually, this is very useful. You would say, like, what do I do with a closed file descriptor? But there are some things you can do. And for this particular bug, we use this to know whether we triggered a race or not. So we have a thread just looking at the file descriptor. And we have the race thread release the file descriptor. And when our thread says, like, invalid file descriptor, then we know we won the race. Then, on the other hand, we have binder objects. And I said in the beginning, they are reference counted. So what you put in there is just a descriptor of the object, this pointer that identifies the object. And then the binder will look up the object, the heap object, and will drop a reference to it because it was acquired during the translation process. So now we have a primitive that allows us to drop references on arbitrary binder objects, at least binder objects that represent arbitrary nodes that we sent through binder. And of course, if you decrement the references to 0, then the system thinks they are not used, and it will free them, and you get the use after free. So what's the high-level plan, to summarize a bit? First, we prefill transaction buffer with fake objects. Next, we free the transaction buffer so that allow user free is 1. Next, we make a transaction which has data and offsets, such that the driver will process the objects that we prepared in there. And we make the sending side fail quickly to make it exit fast and not process these fake objects, because otherwise it will start translating them and it will make a mess of them. And then on another thread, we erase these to cause the free of these objects. And then from the monitor thread, we will be looking to know when we trigger the race, so we can stop racing and continue with the exploit. And after that file descriptor is closed, we will also tinker with reference counts to cause use after freeze. And now we will use those 2 use after freeze to somehow get kernel read-write access, and from there, profit. OK, but there are a few problems. Problem number 1 is that if we raise this thing, and we get to this point here, after the freeing path has reached the free point, it will be set to null, this buffer. So it will have set this buffer to null, and then we crash on a null pointer, the reference or whatever exception. So yeah, that's not nice. We have to make sure that this doesn't happen. There is also a bunch of bug ons that Linux keeps ranting about, but developers keep adding to their code. And this one here was, in particular, the one that was being hit by the fuzzer. But then we have a bunch of other ones that may or may not occur once we enter this buffer free function for the second time. So the first time around, this is all fine. But the second time, this one is set to 1. Transaction is set to null. And then this data may or may not be good. So we have like 5 asserts to get through before we can do anything useful with this. Otherwise, we will crash. And yeah, for our approach to work, we need to be on both sides of a transaction, sender and receiver, because we need to know the pointers, the user space pointers, or well, expected pointers from the binder nodes. And it's also convenient for easier synchronization. It's not like the main requirement is because of the binder nodes. Now, the talking to yourself kind of thing is not really something that happens on Android, not often. Because as I said earlier, if you get a handle to yourself, it becomes a pointer. And you can only talk to handles. So how do we deal with this? But it turns out that the binder driver has, like for them, file descriptors match processes, right? And there are some tricks through, for example, the token manager written down here, which was disclosed in one of the Project Zero issues a while back. With that one, you can get a handle to yourself. Like you can push a handle, and then you can later look up the handle, as long as you know some secret number. So this one is very convenient to make binder allow you to talk to yourself. Now you can have 2 processes that have the ability to talk with each other through binder without bothering anything else in the system. But this also limits us to non-sandbox processes. So the bug was reachable from the sandbox, but we didn't see a good way to exploit it, and we went for this way, which then now, from that point on, we cannot do sandbox escape with this bug, or with this approach. And on top of that, all mitigations, kernel SLR, PAN, PXN, which are the ARM equivalents to SMEP and SMAP, if you are into Intel. And yeah, it was like the Pixel 3 came out right at the time we were working on this, and came out with control flow integrity. And Samsung also has their own flavor on their phones for a while. And on top of that, Samsung has this RKP you heard about yesterday, which also does some protection things that prevent us from exploiting in certain ways. So yeah, it's a long road with hopefully root shells at the end. So the roadmap is, I broke this down into like 5 easy steps. Avoid the null pointer exception, 5 or 6, I don't know. Do I know to count? Yeah. Avoid the null pointer exception first, debug on crashes, then use the use after free to bypass KSLR in some way, so get some pointers to start working with. Then use the use after free again to get read-write access, and then clean everything up in case we corrupted things, and get root. So yeah, number 1, avoiding the null pointer exception. For this one and the next one, there are 2 ways of doing things. And yeah, my way for this one was basically just run some code in fast CPUs and run some code on slow CPUs. If you've looked at ARM, there is big, little architectures. And therefore, you have usually 4 cores that are big and 4 cores that are small, or 2 and 2. And they have different properties. So I played around scheduler properties to just pin different threads to different CPUs, and I got to pretty reliably get through the null pointer, the reference, without crashing. It still happens every like 200 attempts or something, but it's not too bad. So this kind of works, but it needs tweaking per device, and the scientific and proper way of doing this is what my colleague did, which is playing with the contention on logs. And I think in this case it was some mutex contentions where when you release a mutex, if it has waiters, then there are calls into the scheduler. And this allows preempting at the right moment so that you can have a bigger window to do your exploit, right? So this is out of the way. Now onto the bug on crashes. Again, I went for the ugly way, which was, I said that there is this monitoring thread, right? So once this monitoring thread releases a file descriptor, we know that we won the race. So what I'm going to do is I'm going to pin this thread to the exact same CPU as the thread that's going to cause trouble later on, okay? And now I'm going to cause a use after free with my bug, right? And then from that use after free with the monitor, what I'll do is I'll reclaim the object, replace it with some object that has an acquired spin log, and then acquire it. So now we go into a spin log which is non-preemptive, and the CPU completely hangs. But hey, we have 8, so we can fix it later. It's annoying, it's ugly. Like when your leak doesn't work well, or when the other thing doesn't work well, then your CPU is hanging, and then you have to reboot your phone, especially if you're developing the exploit, then this is a nightmare. But there is also the smart way to do this. Again, from Jordan. He saw that, I swear I tried this before, but it didn't work. But anyway, he saw that sending a transaction at the right time would reuse the buffer and would set the freed thing that was causing problems to 0 again. And everything else would match because it was a proper buffer that had been reused. Then it became like a reuse of the freed buffer, like a use after free, but with the right data. So we can pass the whole, the whole set of asserts at once. So this was very nice because I got rid of one use after free in my exploit. So this is what I used at the end when my whole exploit worked and everything. But anyway, so the crashes are out of the way, at least the stupid ones. Now we want to get arbitrary read, actually we want to bypass KSLR. We know no pointers right now. There is KSLR, we know nothing about it currently. So because it's a use after free, we need to do some heap spraying, yeah? Reallocate it with controlled contents. Now, what comes next in the slides? So most known and generic convenient ways to do heap spraying wouldn't work on Android back then. I think many phones came with config keys equals no, which rules out key control-based spraying. sysvipc is usually also no, at least in the common kernels. I don't know if there are kernels out there that use it. And user-fold-fd is also disabled, so you cannot use these nice techniques that are out there. There is another complication that, it's sometimes a complication, sometimes a blessing, but all the objects that are less than 128 bytes, or at least at this point it was like this, all of them would go to the 128-byte kmalloc slab. So it's annoying because, all sorts of unrelated things will come to your slab, but it's also maybe good because all sorts of unrelated things will come to your slab, and you can use them for the use after free. So we went for send message-based spraying. It's a known method. It has full control of, or almost full control of size, contents, and also lifetime if you do it the way that we were doing it. But in that way, it requires one thread per allocated object, kind of similar to the user fault FD, because you have to block the thread so that it doesn't get freed. And this works because send message has a kmalloc up here with a control length, as long as we pass a certain minimum. And then it has a copy from user here with our data, and then it does some things, and then it frees it on the way out. So what we do is we make sure that this blocks somewhere here. And you can just make a full buffer in the socket or things like that. And socket operations there are socket operations that are blocking. So you could block the send message at the right time, and your thread stays there until you unblock it later on. So from there, we need to leak data. We have this binder node that we freed, so that's this target node up here. And when you receive a transaction, there are two pointers that are taken out of that binder node, and they're given to you, to userland. And that's the PTR and the cookie. So, and these are just copied to users, so you can just read them. So what we do is we have to find an object that has something nice to leak at those two offsets, okay? But this is during a transaction receipt, and we are working with transactions to trigger the bug. So, and we have to receive transactions also. So usually, if any thread, if any thread that's a looper in Binder tries to read a transaction, they will get the first transaction that's available. And this will basically make a problem with our bug, because we cannot trigger the bug and keep the transaction that was before it pending. But there is a semi-complicated way of doing that, which is basically having nested transactions. So what you do is you start with one thread, you call into thread B, and then that thread B calls back into thread A, and because it's in the context of an already existing transaction, it goes specifically to thread A, because it could be a callback on an object that thread A provided. So we'd rather have that thread handle it. And the same happens if we do a third transaction from here to this one. It's still in the context of an outer transaction, so we end up queuing these transactions for one specific thread. With this, we can just dedicate this thread to a leak and wait until the use after free has happened, receive the transaction, and we leak 2 pointers, or well, hopefully 2 pointers. I mean, if I leak 2 numbers that are 0, not useful. But now we have to figure out what object to replace this with. So when you have a hammer, everything looks like a nail. So I used IDA. I went to IDA, structure size, and goes by size, and I found this structure that contains a linked list that points to file pointers, which are typically very useful, and I can actually make as many of them as I want, and I can control the lifetime of the structures as well. So now I know a file pointer, and if you see down there, down here, there is a kernel pointer coming out. So yay, we now know a kernel pointer. We bypassed KSLR, kind of. But this was not very stable. I think it was working like 70% of the time, so it was like nice, it kind of works. But then every now and then it would fail, and I wanted this to work properly, especially when I was debugging with this ugly way of deadlocking everything, because it was super annoying to have to reset your phone every 2 minutes. So I traced kmalloc and kfree with the built-in kernel tracing capabilities, and I realized that what was happening was that there was so much time in between my alloc and my free, and there was so much things happening in the slabs that the slab was not, or the freeing, or the reallocating slab was not coming from the same CPU as the previous one. So there are active slabs on CPUs, on each CPU, and it was somehow landing in a different CPU. Originally, I was pinning everything to the same CPU, and this is why sometimes my object moved to a different CPU. Solution, well, easy, just do it on all CPUs, just spray more, make more threads, and bigger orchestra, as they were saying earlier, and that's it. And now we were leaking quite reliably. So yeah, slow progress, but better than no progress. Now I want to get read-write access. So to do that from a leak, it's kind of hard, so we want to corrupt some data. And we look at the rest of the uses of these nodes, of these target nodes. Because we can fake these nodes, we can set the reference count to 1, and then we can free the binder buffer that we already freed before, that has, or a binder transaction that's for that node. And what happens then is that before it releases it, it will do, well, it will do these 2 things. The first thing is a binder DQ work ilogged, which is God knows what. And the second one is an RB erase, which is removing a node in an RB tree. The first one boils down to a list delete, which you also probably heard of if you've been here for 2 days. And the other one, you can make it boil down to some sort of list delete as well. So what we get is 2 AA8BMO primitives, almost arbitrary right almost arbitrary 8-byte mirrored override primitives. The first one depends on config debug list, which is set sometimes, but anyway. And the second one is basically if you set it to set the left part of the arbitrary to null, then you get this. So that means that you get the very same primitive through two different functions. Yeah. If you set it to something different for null, then you just get a cascade of stuff that you don't want to think about. So just simplify, set one to null, and that's the fastest path through the function done. So with these two guys, we can write semi-arbitrary values to controlled addresses. These values, though, have to be writable addresses. And if you've been paying attention, you know that I only know one pointer so far, so that's a bit problematic for now. But also there is PAN, so I cannot fake some of these things in userland, so I cannot write to userland. So we solve this with binder mapping spray, which is basically open many file descriptors, mmap, and then you have, for each of them, a vmalloc buffer. So it looks like this. We have this thing. This is the struct file. We know the pointer to this guy, to the beginning of this guy. Now, we make new file descriptors. This binder FD should be 1, 2, 3, 4, but and then it turns out that this part is fairly predictable. You can predict quite well the vmalloc space, and if you make enough of these guys. And then you just trigger your bug and point it to a guest address within this spray, and now you have an inode and a private data from the file pointing into this, where you can control the data, because this is a binder transaction buffer, so you can send transactions to this process, and the data will come from the transactions. So at the moment, we have an inode and a private data. How do we leak? But first, a status check. We can place arbitrary data at a known location, so PAN is gone for us. We can leak a struct file, and we corrupted private data and finode. And we can fake those structures in the binder mapping by just sending the transactions. We still need to know for convenience which one of these many mappings we created is the one that that it points to. But that's fairly easy because the override is mirrored, and it will modify the binder mapping. So we just scan and we find which one was overwritten. And we learn some pointers on the way, which is always nice to have. Now, when we do this, we can call into stat, or fstat, really, for a file descriptor. And because we control the finode will be pointing to an arbitrary location, and it's passed here. And then there is a dereference of that for the super block, and it will read 4 bytes out. So we can just send a binder transaction, put the SB value to whatever we want, then trigger fstat, and we read 4 bytes. And we just rinse and repeat as many times as we want, and we can just read arbitrary kernel data. And since we had a pointer to start with that points into a struct file, then we can also leak the kernel base, and we can just keep pulling from that and learn the whole address space. So that allows us to basically, bypass KSLR completely. All we need now is an arbitrary write. So there is light at the end of the tunnel. All right, so how do we get an arbitrary write? Well, I use the private data for that. Private data is the opaque structure in a struct file that is driver specific. So if it's a binder file descriptor, this is a binder proc. If it's, I don't know, whatever other type of file descriptor, then this is whatever this driver is using for representing the file descriptor internally. So for binder, there is this binder proc, which contains an allocator inside, which contains the buffers that binder sends transactions to. And those buffers, they contain, this is not now, I don't know where my mouse is. Well, they contain this data pointer that is exactly the address where the copy from user will be performed on sending a transaction. So all we need to do is we need to fake these few links in the binder mapping and then send a transaction. And then the transaction will basically write whatever data we send to the transaction will be written at the address that we control. And we have an arbitrary write. We also learn a couple other pointers again. But this gives us, this broke. That's nice. Anyway, this gives us the right primitive. So what we need to do now is, get root, right? So we first set cell Linux enforcing to 0. Oh, now this is going by itself. We then find init and steal its credentials, not so much for the fact that it's root, because we already know it, but for the cell Linux context, and maybe there is other useful stuff. We clean up, and in my case, this meant cleaning up the deadlocked CPU, so only at this point I can actually get rid of that stupid stuck CPU. But this was like maybe 1 second or something of deadlock if everything works fine. And then, oh, what's happening? Somebody's messing with me. Do I really need to disable Bluetooth? Turn off. Done. All right. What are you seeing now? The other thing. Oh, these MacBooks are useful. What's happening? So I kind of lost my presentation. Is it here? No, I'm getting confused. Sorry, guys. It's actually there. That was actually the presentation, I think. Right, so this went forward without me talking, so then I got confused. Release the deadlock CPU, and then remember we have these send message threads that are blocked. On the way out, they're going to free these buffers. And we use some of them for binder free, which frees the buffer as well. So we would have a double free if we don't clear the references. So we just have to make sure to find wherever send message is storing its reference and make it null. And then we will be able to pass we will be able to survive this. And then we start a reverse root shell. So now is the moment of truth. This is a video, but that's not what you're going to see, because I have some faith in the demo gods still. Is it, again, the video? Damn it. I don't know how to use computers. No, it's open. And there is this thing, which is a phone, which is here. I have to unlock it. I have to show you what it's running. It's running Android. It's running Android version 9, and I don't know if that's visible from the end. I'll read it out loud because this thing doesn't work anymore. It's December 5, 2018, so that's when we were working on this. And here there is a shell, but I don't want the shell. I actually want logcat. All right, so yeah, I just press here, go to my exploit, and press spawn and see what happens, and hope to be lucky. It works most of the time, so. Right, we're now trying to trigger the bug, and we're leaking pointers and stuff, and the application didn't crash. It was me that clicked something, because when the phone is active, it's actually faster to win the race, and I'm impatient. But I got a connection back, and you see some leaks coming through in the logcat window, so like all the kernel addresses, etc. And we can see here, well, we can do ID here, and it says we're root, and we can get enforced. And yeah. So that worked. Now, there is a bit more. I hope you're soon seeing the presentation again. This one? Is this it? Yeah, I need to move. There. Oh, it's not it, I think, or I moved the wrong thing. As I said, I don't know computers. It's crashing. OK, well, I'll say it out loud while it recovers. Here we go. So are we done yet? So there is this, we said that we wanted to do this on the Galaxy S9, so there is list config debug list is set, which means only one of the two arbitrary write primitives is available. Luckily, back then, there was no panic on corruption with that feature. So it would just warn on the kernel logs, but it would not panic. So it's like, oh, the list is not good. OK, I will go through. Then I use the private data one to, so I overwrite private data for a binder file descriptor, and then I figured a way to make a second arbitrary write from there, and then corrupt further things and get to the same spot. And then also another complication is that it was using an old driver, CVE 2017-13164. 2017, we're September 2018, right? What happened? Well, what happened was, I think, my understanding of what happened is that this CVE is in the Android security bulletin for Pixel phones. Pixel Nexus phones. It's not on the generic one. It's on the Pixel phones, which means that many OEMs, because it's on the Pixel phones, it's not my problem, so I don't port it. So that is, for us, that is good and bad. That means that we can, so this bug in particular was putting these binder buffers inside the binder big buffer, including the next and the brief pointer and everything, so we could see all these kernel addresses. But we can also see all the metadata of the allocator, so we know precisely when the buffer is being allocated and deallocated, which means that I can also get past this null point. Like I have more timing information, so it's easier for me to get through the null pointer crashes as well. But I cannot use my write primitive because this implementation had inline buffers and not out-of-line buffers. So I had to change this and do kind of ROP, or actually not ROP because there is some checks, but it's function-oriented programming, let's call it like that. And Linux enforcing is read-only, so we cannot do like disable Linux, we're done, go. But I just reloaded some Linux stuff, and also at that point, Samsung had, I think by mistake, disabled part of the credential protection for a few months, I think. So I could just override it. So now it's like, yay, we're good. Except this happened. If you're familiar with the Linux kernel mailing list, this looks very similar. And I cannot zoom in anymore, but up there, it says 6th of November. And I got to finish this thing by like at the end of December, so I was like, damn it. So yeah, this was Miguel's face, mostly. So at this point, we were like, well, got fixed. Too bad. We spent an extra month, and it's annoying. But we thought it's probably Project Zero, and it turned out a few months later. This cannot be seen on the screen, but this is March. 6th of March is written up there in sort of Chinese, but I guess that means month or something. 6th of March of 2019. So. These guys from 360, they published a post, which was, of course, after Google had published the security bulletin, so now it's fixed, and it's in all Android phones, right? They were the ones to find the bug, but it was actually also Project Zero, so Jan Horn found it. And, well, the part that makes me feel at least a little less bad is that down here, it says reported on the 23rd of November of 2018. So at least I'm not the only one who's not reading the kernel mailing list and missing that, there are all bugs. What's my timing? Oh, plenty. So yeah, this was a bit the story. Now I want to look at it at the bug, or at the way the guys from 360 exploited the bug. And of course, I don't have their exploit. So this is all based on pure speculation, based on their presentation they made at Hack in the Box, which had most of the details, but if you don't try to re-implement it, then there are some details that are always kind of missing, that you don't really understand. So they don't use this way of doing like this, allow user this freeing of objects in the binder transactions. They just go for a pure use after free on the heap right away. And that's on the binder buffer structure. So this binder buffer structure, they sometimes reuse the old one, but they sometimes make new ones and free the old ones, depending on whether they are like adjacent buffers that you can reuse, or it's an allocator, and sometimes it's like, okay, this buffer in the middle, now I can merge with the other two, so I drop this one, and stuff like that. And that will basically make a use after free on that buffer, because it really goes to the heap, and then you can use it for your transaction. My understanding. Well, so first of all, this should work from the sandbox, because you don't need control of both ends, or tricks that I don't know about to do that from the sandbox. It also, I think it requires triggering the race or use after freeze for each read-write access, I think. And I think this because, so maybe you can do with the race once, because they will reuse this buffer many times and whatnot, but I believe at least to be able to read and to write, they have to send a new transaction, which should be a free buffer that they control, and therefore every time you have a use after free for everything that you access. And in our case, we did one race win, 2 use after frees triggered from that one time, and then we're done with it. We don't need to trigger the race, so hopefully this is faster. They also use a service that echoes data back to the process, and this is how they go around the limitation of being able to talk to yourself. So they send some data to the servers, then they trigger a bug while they call, this function that gives the data back, the same data that we produced. And that allows them to use an arbitrary write. It's very similar to my arbitrary write, but it's abusing the fact that the server is giving back stuff that you control. And as far as I know, this service is not reachable from within Sandbox, so that drops, again, the possibility of doing a Sandbox escape. And you'd have to find something similar on the Sandbox. They also use a Qualcomm-only driver for leaking a struct file. I'm pretty sure this shouldn't work from Sandbox, and if it does, it's a bug in itself, probably in the Sandbox profile. And it's also not generic in the sense that you cannot use every Android phone and use this Qualcomm-specific driver. They also played with scheduling and mutexes to improve the odds, so they were not as dumb as me to just do this weird deadlock, and they were much smarter, like my colleague. They also seem to pin to CPUs to improve their chances, and that's also not allowed on the Sandbox, so another requirement that drops the Sandbox exploitability of this, although you can probably work around it. So my overall feeling, and I'm probably mistaken about this, is that it seems ours is a little faster and more reliable, but could probably be not. But theirs has the potential, their approach has the potential to be a Sandbox escape, which ours definitely has not, without an additional bug to be able to talk to yourself. And they were first, so they win anyway. And in terms of closing conclusions, that writing exploits, modern exploits, can be a pain. It's still possible, but just do not despair if you're trying to learn this. But fragmentation is kind of annoying. So we had this bug that was in the core of Android, but we ended up writing two fairly different, similar approach, but fairly different exploits for two different phones. And I'm pretty sure if we took another phone from another brand, we probably had to change something as well, even if we didn't rely on offsets from the kernel base or stuff like that. We'd resolve everything on runtime. I think we would probably have to write different exploits just because of differences in the kernels. And it's really easy to go down a rabbit hole, and it's good to keep in mind that there are probably better solutions than the one you're working on right now, and take a few steps back, think about what you're doing, and try to find the best solutions. And the common conclusion when we're talking about many things, including Android, is that there is a pretty large patch gap. In this particular case, I think this was 4 months from the upstream kernel fix to the Android bulletin. So that's quite a long time. And then, of course, not everybody fixes this on the day one, so there is quite a long window. And with this, I want to do a little video on special request from Miguel, and then I will be open for questions. So in case you don't see this, that's February 2020 over there, and the video should be playing, but is it? It says it is. Now it is. Old computers. So there is no SU, we cannot, with Linux is enforcing, we run this thing. It's not the phone crashing, it's just going to sleep. That's why I clicked in there. And, well, kernel base, ID, blah. So that's a wrap. Questions?
Thanks for your talk. First question, as I understood, you fuzzed, with fuzzing you found bugs which Sysbot didn't find, right?
Correct.
So you used some tricks for your fuzzing, I guess? Any details or no?
Just definitions were not proper enough. That's...
another question.
Go ahead. So the syscaller definitions were not good enough to find these bugs. That's the only thing I can say.
Okay, thanks.
No, you had another question. Go ahead.
I have another question. So yesterday, Mehdi told us about ListDel.
Yeah.
The fact that there is no safe unlinking. You show us another bug, use of the same kind of.
So safe unlinking. Yeah. Go ahead.
Is it going to be introduced, or is it just too slow to add safe unlinking in the safe? Because this is done on most OS on the desktop. So why is it not done on the Linux kernel? Do you have any idea? No.
I mean, it's depending on the config of the kernel. It's of course slower because you do checks and stuff, but there is a config that's config list.
But it's not by default. So
I don't know.
it's
Maybe
like-
now Android put it in the common kernel. That can be. Do you know?
They're working on seeing if it can be enabled.
Yeah, because the way this works, there is the Android common kernel, which is a fork from upstream, and then from like LTS or whatever, and then there is the fork from each vendor, which adds its own drivers and changes everything in between, and adds all sorts of security features. And yeah, the config files typically extend from the ones that come from common kernel. And what happens is that often these people just stick to one kernel for the whole lifetime of a device, and they don't upgrade to newer lines anymore. So it takes a little while.
And you mentioned those bug-on checks, and if you hit it, is it in the
Crash.
process context, so process crashed, or it is in a kernel you have panic?
So it's a panic. I think it's technically an oops, but there is this panic on oops thing. So in Android devices, in practice, this means that just a complete crash of your kernel and a reboot.
Okay.
Any questions?
Anyone else? No
Over
running?
there.
Yeah, running.
So you said Samsung accidentally disabled RKP on something important. Can you speak more to that?
No, it's config of the kernel. And that's fine now. So no worth talking about it anymore. It's fixed now. So I think it's accidental. I mean, don't know more than that.
Was the method used similar to that reboot one, the power command off method? Or
Sorry, I don't.
what
Really,
was your method for disabling RKP?
it was already disabled. Let's say for
Completely
the
disabled.
credentials. So they were not read-only in this case. I don't know why. Just at that moment, I didn't investigate it further because the bug got fixed, and
Gotcha.
Anything else?